See that wiggle? I see it too. That's exactly what we're working on solving right now. We are in the midst of using OpenSCAD to develop a 3D model that's going to be 3D printed to fit in the middle of these two boards to provide some stability, but also to provide some hex pockets so that we can actually screw in our leads to this LED driver board. Now, if you haven't seen the previous episode, I highly recommend you go do that because we are going to pick up exactly where we left off. These two circles were created in OpenSCAD. On the other side of the circles are the two hex pockets that are basically going to cover these two terminals on this LED driver board. The code that we use to create it looks like this. We have a number of parameters, including the fit gap that helps us make sure that real-world parts will fit into the 3D model that we print, a minimum wall thickness, which basically describes the minimum resolution our printer is able to print in three directions, X, Y, and Z. The proportions of our hex nut. In this case, it's a 3.5 millimeter radius with 2.3 millimeter thickness, or what I'm calling intensity. Two vectors which tell us where those hex nuts are supposed to be, which line up with these two terminals on our driver board and are referenced to the bottom left corner of the board. And a few special parameters which help define the smoothness of curves and also help the rendering of objects within OpenSCAD. These hex pockets are subtracted from this surround material, and then the whole thing is rotated by 90 degrees along the x-axis. And you can see the resulting hex pockets inside those two circles. Now, the first thing that we're going to do as we jump back into this is a little bit of parameter housekeeping. The radius and intensity of these two surrounds that you see here are created based on the measurements of the hex pockets that's inside. We're going to discover that those values are very useful in other parts of the code. So rather than always going back to first principles and using the measurements of the hex nut as a source to recalculate all those, what we're going to do is we're going to create another parameter that's calculated at runtime, and then we can use that calculation throughout the rest of the code. Watch. I'm going to call that calculated parameter p hex surround, which is basically the proportions of the hex surround. And what I mean by hex surround is that material right there. So I want the actual radius of this surround and the intensity or thickness of that surround. And to get those values, we're using the radius of the actual hex nut, adding that minimum thickness to give it some supporting material around it, and that little fit gap, which makes sure that a real-world object can fit inside a 3D printed object. The intensity is done in the same way with the measured intensity, an extra wall thickness, and that fit gap. We package that whole thing up into a proportion object, which we're calling p hex surround. I'm going to give it a comment that tells us that this special parameter is calculated at runtime. And that means that this calculated parameter won't show up in our parameter list. So it doesn't matter that I've used the special formatting to make it look like it's going to show up. It still won't. Now that we've defined the calculated parameter, we can start applying it in our code. There's one location. Here's another. And another. I can apply it here as well. The next step is we're going to create two more parameters that are going to define the thicknesses of the edge and the front of our part. Remember, the part is going to snugly fit around this driver board. So right over here, the part needs to have some thickness, and we also need to have some thickness in the front. We're going to call this the flank edge, and we're going to call this the leading edge. So in our code, I'm going to add a new section in the parameter list called scalars, where I will include our leading edge. I'm going to give it a value of 2.4 millimeters, and I'm going to prescribe the precision of that value to make sure that it never goes below 0.8 millimeters. It can increment or decrement at increments of 0.4 millimeters, and the max it can go is 5 millimeters. I'm going to apply the same precision to the flank edge value, but I'm going to preset it at 1.6 millimeters. So basically, the front or the leading edge of our part is going to be slightly thicker than the side or the flank edges. And what we want to do with those parameters is extend these circular solids so they cover the leading and the front edge. But of course, we're not simply going to scale the circle. I'm going to add some interest to that shape. And in order to do that, we're going to move away from our primitive creation of a circle and create something which has a little bit more power, a polygon. Under our cheat sheet, you'll find polygon in the 2D area over here. And we're going to use the first iteration of polygon, which basically requires you to include a list of points. So I'm going to start creating that polygon right in here inside this linear extrude scope. And that basically means that although this polygon is going to be created in 2 dimensions, it's going to be extruded to the same level as the hex surround. The x-coordinate of the first point of the polygon is going to be located at the center of the first terminal plus the radius of the surround. And the y-coordinate of that point is going to be in the center of that terminal. And so if you look at our model, it's going to equate to around here. And then I add the next point of that polygon. This one is going to be in the same x location, but the y is now going to be minus leading edge. So in our model, if the first point is here, the next point is going to be straight down in the y direction around this location, just below the x-axis by the same value of this leading edge parameter. In our case, it's going to be 2.4 millimeters. That point is followed by another point at minus flank edge, minus leading edge. So the y location is also going to be just below the axis over here, but the x location is going to be around here. So just to the left of the vertical axis by exactly 1.6 millimeters as we've indicated in flank edge. And our final point is going to be at the same x coordinate, but we've brought it back up to the center of the terminal. So there's 2 things that you should be noticing here. One, all we're doing is we're making a simple rectangle with 4 points. That part's easy. The other thing you're probably noticing is that I'm referencing this rectangle using x and y coordinates. But in our model, the y coordinate has somehow been translated into the z coordinate. Remember, in our 3D space, x is this way, y is this way, and z is this way. But in our polygon, I'm defining x is this way and y as this way. I can do that because of this rotate instruction over here. Remember, every 2-dimensional object in SCAD is created flat on the XY plane. So when I'm describing the X and Y locations, I literally am describing the X and Y locations on that plane. But because we've rotated this whole thing 90 degrees along the X-axis, that Y direction becomes the Z direction. So I mentioned this in the last episode, this confusion of of axes before rotation and after rotation is critically important, and you have to keep them in your mind when working on these 3-dimensional models. And when we render that, sure enough, we see the rectangle that we're pretty certain we were creating. Now there is a primitive called square in the cheat sheet if you look it up. There it is. But we didn't use it because polygon is way more powerful than using the square primitive. You'll see why in a little bit. And we can't forget about the other side. The other terminal also needs its own rectangle. Now notice when we created the left polygon, we didn't define the width and height of that polygon. We simply located the points of that polygon and let it create it. So if we're going to locate the points of the other polygon, which is going to be on the other terminal, we need to know where to put those points. So for the left point, we used that concept of left flank. So we wanted it to be 1.6 millimeters away from this edge. So if we want the same thing on the other side, 1.6 millimeters away from this edge, well, we have to know where this edge is, which means we have to define another variable which describes the breadth of the board. The breadth of this board is 28.4 millimeters. Notice the B prefix. I'm going to add a comment up top helping us define what the B stands for. Now, along with that B, I've also kind of defined a west and east direction. This is a lot less arbitrary than left and right, because if I'm looking at the object from the other side, well, left and right become right and left. And so in order to avoid that, I'm going to use the directionality constant of west and east to differentiate between sides of this. And so what that means is I want to change the definition of my terminals from terminal 0 to terminal west and terminal 1 to terminal east. Now we can create the polygon for the east terminal. So we're going to follow the same principle, the center of the east terminal minus the hex surround, because of course now we're talking about this side, which is negative in the x direction, followed by the point directly below it, traveling towards the east. Now we're using our B board parameter plus the flank edge, which will accurately put us on this side of the board. and then complete the rectangle back up to the center, the Y center of the east terminal. By the way, pay close attention to the double square brackets around the polygon. The polygon instruction wants a list of points, and since a point is just a 2D vector, which in itself is a list, we're giving it a list of list. When we render this, yay, we've got our other polygon. You can even spin this around a little bit and see, oh, what's going on over here? We suddenly have this new strange visual anomaly showing up. It's almost like I can see through my part. Yeah, this showed up on the last episode, right? We need to increase our convexity integer to help OpenSCAD render this properly. And our convexity integer is right here, fx0. We have it set to 2. Let's up it to 3. And like magic, that visual anomaly disappears. In the previous video, we talked a little bit about finding efficiencies, where you can reuse bits of the code so you don't have to keep writing the same thing over and over again. Well, down here, we're creating 2 hex pockets, and the only difference between those 2 hex pockets is the translate. One is located at the west terminal, the other is located at the east terminal. Well, if you're familiar with programming, you might have heard of this thing called a for loop, where you can iterate over the same code multiple times. Well, we can use a for loop in OpenSCAD to create a circle any number of times. In this case, we'll create it twice. The cheat sheet highlights all the various ways you can use a for loop here under the flow control section. We're going to use the method of discretely identifying each instance of the loop. So here we have our variable. This truly is a variable, unlike the parameters and the rest of OpenSCAD, because we're doing a for loop, and in a for loop you have to iterate a number of times, which means you need to have a variable that changes with every iteration of that for loop. And in this case, our variable is v, and we're iterating it over these 2 possible values, v terminal w and v terminal e. And the line that's going to be looped is the first one here. I'm simply going to change the prescribed location of v terminal w and turn this into our variable v. I can then remove the next line and render it. And sure enough, both hex pockets are still showing up. If we go back to the hex pocket surround, we're creating a circle and a polygon twice. But remember, those polygons are not exactly the same. Although they are 2 rectangles, because of their relative positions, they are mirrored from one another, and that's visible in the model right over here. So although we could include those in a for loop, we'd have to make some changes into how those polygons are located. And in my opinion, those changes aren't worth the end result of just saving a few lines of code. I mean, we're just creating 2 polygons. So my opinion is we just leave it alone as is. The circles, however, that one is very easy. We'll insert a familiar for loop, which has our v variable that iterates between the west terminal and east terminal. Take one of our circles and adjust the translate vector to the new variable, and simply remove the other circle. Rendering it results in no difference, which means it worked. But you know, I'm not a big fan of these pointy edges over here. Let's smooth them out a little bit with what's known as a chamfer, or a 45-degree slope, to kind of slice off those corners. This is where the power of a polygon really comes in. We're going to need a new parameter to determine how much to slice, and I'm going to call that r corner. I'm going to set it to 1.6. R, of course, means radius, so we're going to want to include a comment to define that prefix. Then looking at our model, identify which of these corners I want to chamfer off. This corner right here was the 4th and final point in our polygon. So rather than having that point come all the way to the top, I'm going to subtract our corner from that value, like this. And then of course I have to add another point, which basically is the same point over here, but pushed in the positive x direction, also by r corner. And you can see that done here. And when you render that, nice chamfer. Let's do the same for the east side. Beautiful. If we used the square primitive, we would not have been able to do what we just did. These hex pockets are starting to look a little bit nicer, but they're still not fulfilling their purpose. The hex pocket is only useful because the hex nut that fits inside that pocket is used to anchor a screw. Now, when that screw gets fastened, eventually it's going to come out the other side. And our hex nuts do not have a cavity to accommodate that. And what is that cavity going to look like? Well, it's going to be cylindrical to allow this screw to fit in. Looks like we need to define a new proportion parameter. Let's call it P fast shaft, or the shaft of the fastener. I'm going to give it a radius of 1.36 and an intensity or length of 5.8. I did not make those values up. I used a micrometer to measure them. Now to create the cavity, we're going to use our first 3D primitive, a cylinder. We can create a cylinder in two ways, by providing the height, or what I'd like to call the intensity of that cylinder, and the radius or diameter of that cylinder. That's one way to create it. The other way is by providing the height or intensity of that cylinder and radius 1 and radius 2, or diameter 1 and diameter 2. The primitive of cylinder in OpenSCAD allows you to create straight cylinders, or even cylinders that increase or decrease in diameter. Now, our cylinder that's going to accommodate this fastener is simply going to be a straight cylinder, so we'll use the first one. We want to create the cylinder within the difference scope. Remember, we're not creating a cylinder solid, we're creating a cylinder that's going to be subtracted from our solid. So we can define the fastener holes immediately below the hex pocket. Since there's two of them, we'll use a for loop and translate a cylinder for both of those locations using this V variable. The cylinder is created using the intensity of the fastener shaft plus a fit gap, just to make sure there's a little bit of wiggle room in its intensity. Then we call the radius of the fast shaft proportion for the radius of our cylinder. And then we want to add a fit gap times 2 to make sure that this thing has some wiggle room on either side. And of course, because this is a curved object, I'm going to include the FA and FS parameters, which will ensure that the cylinder is sufficiently smooth. Then when we render that, there's our cylinder holes. Now we can clearly see the holes that were made from that cylinder, but we can't actually see the cylinder itself, of course, because it was subtracted from the solid. But is there a way for us to kind of confirm that the cylinder was created with the appropriate dimensions of that fastener shaft? Yeah, there's actually a really neat modifier that you can use in OpenSCAD to show objects that are supposed to be subtracted. In the cheat sheet, you'll find this modifier I'm talking about right here. This is the highlight or debug modifier, and it's simply a hashtag. So in the code, if I place a hashtag on the translated cylinder instruction and then render it, suddenly I can see our cylinder. Now, wait a minute. That is not a straight cylinder. That's because we didn't look carefully at the cheat sheet. See, in the cheat sheet, it says that if you want to have a straight cylinder, then in order to do that, you have to exclusively call out the R value of radius, and then it's going to use that radius for both ends. It's as simple as doing that. Now, when I render it, the cylinders straighten out. But it's still not perfect. It is visualizing the proportion of that fastener shaft, but it's not accurately visualizing where that fastener shaft will be. See, when this fastener is inserted into that hole, it's going to be seated like that, which means we need to consider the thickness of this printed circuit board because the fastener is going to be seated on top of it. So let's add a board height parameter for that value. These printed circuit boards are standard 1.6 millimeters thick. And because I'm introducing a new H prefix, I want to make sure that I include comments to describe it effectively. Oh, the other thing I forgot to mention. Practically speaking, although this fastener will be seated like this, there's usually going to be a washer situated between the head of that fastener and the actual PCB board. That washer is useful because, you're twisting that fastener in and you don't want to damage the PCB board. The other thing that's happening is that washer is going to hold the spade connectors in much better. So we're going to create yet another proportion to define the radius and intensity of the washers. I'm calling it P wash sink. Here is the actual washer. It has a 4 millimeter radius and a 1 millimeter thickness or intensity. Now we can include that value into the translate, but we're going to have to do something about this first, because right now we have this variable v, which is a placeholder for those terminals. But those terminal vectors only include two dimensions, the x and the y, which of course after the rotation becomes z. And the offset of our fastener is actually in the third dimension. So we don't have to worry about breaking apart our for loop. We can actually just break apart that vector and include these our new proportion into the third dimension. Watch. So rather than having it say v, we can break it up into v.x, v.y, and our board height minus the washer intensity. When we render that, Notice the cylinders then adjust in this dimension, or the y-axis, to its rightful location. And we see that the portion of that fastener that actually sticks out from the end of that hex nut is not actually that much. Now, it may not be that much, but it still could potentially be some exposed metal, which we really don't want. So I think we want to be able to cover that exposed metal with some more material. So we're going to create some shaft extensions to make sure that that hole gets adequately covered. And we can calculate the proportions of that extension quite easily. We just start with the radius of that shaft and add a minimum wall thickness and a fit gap, and we multiply it by 2 because we want to make sure there's enough wiggle room within the fastener, and we want to have this cover to have some sort of stability. So I want to have a double wall thickness. The intensity of that shaft, we can add another wall thickness, a fit gap, and then we want to subtract the existing thickness of that surround plus the thickness of the board plus the wash sink. Now that we've calculated the proportions, we can start writing the code to create those extensions. Same as before, we'll use a for loop since we have 2 extensions. Translate those extensions to the right location. Notice we're using the X and Y of the terminals and the Z of the surround intensity minus this epsilon value to make sure that we don't have overlapping faces. And then we create a cylinder with the intensity of our new calculated extension. Make sure we include the R equals so that we get a flat or straight cylinder, and use the radius of our new calculated extension. And then we need to remember to include this in a union scope. And that's because this shaft extension is actual material that we will be adding, not taking away. So by including it inside this union scope, the hex pocket surround and the shaft extension will be unioned into a solid from which the hex pocket and the fastener holes will be subtracted. When we render it, there is our beautiful extensions. In the view menu of OpenSCAD, there's a mode called Wireframe where we can actually see everything inside. Now, if yours doesn't immediately show the wireframe, you might have to re-render your object. And I don't mean preview, I mean render. And that's this button over here. So just hit that render button, and you may need to highlight the wireframe once again to see this. But now with this wireframe selected, you can actually see where those vertices line up. And if we position this model the right way, you'll see how the hole ends up just a little bit behind the extension, which means it's being covered by material, and the radius of the extension sufficiently covers the radius of that hole. Now you may have noticed when we make those little extensions, we're actually creating a portion of this model that's going to be quite difficult for our 3D printer to print. See, the overhangs of this extension right here will be a great challenge for our printer. Now, we will need to do something about that, but we don't have the skills to do it elegantly yet. So we might cover that when we cover the more extreme advanced techniques in the next episode. So hold off until then. For now, we'll just move on. Let's add another simplification to our code. You notice how these fastener holes here are basically made with 2 lines of code, but the hex pocket actually takes 3 lines of code for essentially doing the same thing, except that the cylinders are 6-sided rather than smooth. Well, when we created the hex pockets, we actually created a 2-dimensional circle and then linearly extruded that circle into the shape of this hexagonal cylinder. Well, we can actually avoid all that by creating a hexagonal cylinder using the 3D primitive of cylinder, because this FN business over here, which tells OpenSCAD how many sides this circle must have, that FN value also works on cylinders. So first, we can break open this translate vector to include the epsilon value that's up here. Then change this circle into a cylinder. And since cylinder wants the intensity first, we will have to insert that and make sure that we call out the radius with an R equals to make sure it's a straight hexagonal cylinder. Then we can remove the original translate and the linear extrude line up here, get rid of the closing parentheses, and tab that back, and our end result is identical to before, which means it worked. Now, once we've done that, we've opened up yet another efficiency here. Look at this, the hex pocket and the fastener holes are both using the same for loop. So there's no reason to use 2 separate for loops for the same thing. We can throw all of those into one for loop. Remove that, insert that, tab that. Let's move on to the next portion of our part, which is going to be sandwiched in between the driver module and the controller board. The part in between these two boards. We're going to need a bunch of new parameters for this. The first is pretty obvious. It's the distance between these two boards. I'll pop the new parameter in right here. We'll call it H spacer for height, and it's been measured at 4.2 millimeters. We're going to leverage the polygon command once again to create this portion of the part. If we separate the boards, we can get a better view as to what this part is going to look like. The polygon on this side of the driver board is going to go around this terminal, around that terminal, then back up and around the thermal conduit, and then back down again. We're going to need to know the vector that locates the thermal terminal. We're also going to need to know the radius of that terminal, along with the radius of these terminals, and the thickness of the material behind the terminals. The original design will give us the vector for this thermal, 15.4 by 13.6. So I'll pop that into the 2D vector area here. I'll also add in a trailing edge thickness. We're going to set that to 1.6 millimeters. And here's the radius of the terminal and the radius of the thermal terminal. For now, both are 5 millimeters, but I wanted to create separate parameters in case for whatever reason they need to be different. We'll create the polygon for the spacer just below the shaft extension. It's going to be translated appropriately on the other side of the board plus the fit gap, and of course here's the height of that spacer, and then we linearly extrude it by that same height. And here's the polygon. Rather than going through it line by line, why don't we just render it and we'll see it. Well, that's a nice looking spacer, although it doesn't quite look complete. It appears to be missing the thermal connector here and also the cuts that are going to reveal these terminals. The curve for the thermal terminal is fairly straightforward. We can just create a circle and include that into our polygon. We'll pop it in right after the polygon. It will be translated appropriately. It's going to have the appropriate radius plus a little bit of a minimum wall thickness, and of course our FA and FS. This is within the linear extrude scope, so both the circle and the polygon are extruded together. They are the same part after all. Rendering that. Here we go. It's a great start, but it needs a hole. We already know we can subtract a cylinder from that solid to create the hole. The problem is the fasteners we've been using so far are too short to make it all the way through both boards. So in addition to the parameter that defines the proportions of this parameter, or this fastener, I have to create another parameter for a longer fastener, which means the existing parameter needs to be renamed, and then we can add in a new parameter with some identification to show that it is longer. There's the parameter for the current fastener. I'm going to rename it to pFastShaft064, indicating that the nominal length for these screws is 6.4 millimeters, or a 1/4 inch. Now I'll add a new parameter for pFastShaft095, 9.5 millimeters, or 3/8 of an inch. With that done, we can now define the cylinder that will be subtracted to create the hole. Notice how I'm translating this cylinder. It's going to the X and Y location of the vector that points out the thermal terminal. I'm going to position it at the beginning of the board plus the wash sink. The fastener's also going to use one of these washers. And then I rotate it by 180 degrees. You'll see why when we render this. And I'm using our new parameter to define the proportions of that cylinder. Now when we render that, there's the cylinder. You might already be able to see why we rotated it 180 degrees. Remember, all objects are created in the positive Z axis, and then we've rotated this entire thing by 90 degrees, which means that cylinder should be created in the positive Y axis. But because of the way this fastener is going to sit on this part, we needed to rotate that shape so it aligns to where that fastener will actually sit on our part. Compare that to the other fasteners, which will sit like this. The thermal fastener will sit like this. With the thermal hole complete, we can now move on to the terminal guides, which are the openings to allow attachments to these terminals. Now we could take the approach that we've been taking so far, is to take a circle and combine it with that polygon and then cut that out of a solid, and that will give us the curve. But I'd like to try something different. I want to create an arc. However, examining the cheat sheet reveals that there is no arc function in OpenSCAD. So we're going to have to custom make it. Let's identify the basic components that make up an arc. Every arc will have a starting angle, an ending angle, and a radius. If we think about this curve as just a series of closely spaced points, well, we could use a for loop to create all of those points in the arc. And those points are basically connected by straight lines. That is, after all, how all curves in OpenSCAD are created. Basic trigonometry will give us the vector for each of those points. And we can stick that into a for loop like this. We create a polygon and then iterate the angle for the entire arc. In this case, it starts at 0 and goes to 180 degrees. And we repeatedly create a vector based on the trigonometry that we just defined. Now that polygon will have to be translated appropriately. So we're translating it to the west terminal and then the appropriate Z location, linearly extruding it by the same height of the spacer plus double the epsilon value to avoid the face overlap on both sides of the spacer. And of course, our convexity integer. Let's also not forget to include a comment for the angle. And rendering that, look at that. We see a beautiful arc. That arc looks awfully smooth. In fact, a little bit too smooth. If you notice what we've done, we've basically gone from 0 to 180, and the step value, or the default step value in a for loop, is 1. So that is every degree it is creating a point. Well, we've already defined our minimum angle parameter, FA. Why don't we use FA as the step value? To define a step value in a for loop, we simply insert it right here. Rendering that. Oh, look at that. Now we can see the individual segments of that arc. Now we could stop right there, but in every other curve in our code, we've used a combination of FA and FS to determine the smoothness of all the curves. If FA is the minimum angle and FS is the minimum segment size, and since the step value for our for loop is based on angles, we need to convert the FS to an angle and then determine which one to use. Well, the formula to turn FS into an angle is pretty straightforward. Looks like this. And then we can use the max function to choose whichever one of these is larger. Now, when we render that and try adjusting our FA and FS values, we can see the difference that it's making. That arc was a portion of the polygon. We also need to include the bottom 2 vertices of that polygon here. So we'll add 2 more points to our polygon. And rendering that gives us the terminal guide we were looking for. Now I could put this whole thing into a for loop to do the other terminal guide, but we're going to explore another method. We're going to use the mirror instruction. To use the mirror instruction, we basically copy and paste the polygon command that we already have and then modify it using a mirror. This instruction says mirror this polygon along the x-axis. And don't forget, we have to adjust the translate vector to the east terminal. And then render that. And there are both of the terminal guides. Now that we have this fancy way to create arcs, I'm going to use those arcs to smooth out the corners of our polygon. These 2 corners are the ones I'm talking about. Let's start with the northeast corner. This point right here is that northeast point in this polygon. So if I change that point to an arc, we should have a smooth corner. Let's try it. I'm going to create an arc that goes from 0 to 90 using our fancy step function. And note the radius for our arc is our corner. Now, if I render this, ooh, that doesn't look right. Let's try to get a better view of what's actually happening here. If we use our hashtag modifier, we might be able to see the problem. Now that gives us a better view of what's going on. Look, there appears to be an arc over here, but it's not in the right place. And that makes sense because these translate vectors are at 0, and every single point in this polygon is located using absolute vectors to where it should belong. But our arc doesn't have any sort of absolute translation. In fact, this arc is being created around the origin, which is exactly where that arc appears to be. But since each point is being created inside the for loop, we need to be able to apply a translation to every single point as it's created. And we can do that right in the for loop by simply adding a vector that will translate it to the appropriate location. I'm going to remove our hashtag and render it. That looks a lot better. Let's do it again on the west side. This here is the northwest point. I'll change that to a for loop. This time the angle goes from 90 to 180. And the translate vector appropriately identifies the northwest corner. Rendering that. That is beautiful. Let's move on to the next portion of the part. To demonstrate this properly, I'm going to reattach the module to the controller board. The portion that we're working on right now is going to be the piece that rests up against the controller board right over here. It's not a very big piece. It's basically just the thickness of that controller board, which means, yep, we're going to need another parameter. Now we already have a parameter for the height of the board, but that is for the driver board. So let's do a little bit of renaming to differentiate between the driver board and the controller board. Now we can add in the height of the controller board. We also need a parameter to determine how far the edge is from the center of this thermal terminal. We know that to be 5 millimeters. Another interesting point to note is that this edge doesn't completely clear the terminal. So that edge is going to land somewhere in the middle of the arcs that we just created for our terminal guides. And using some basic trigonometry, I was able to determine the angle between the thermal vector and the terminal vector. And now we can create the shape for that controller rest. And you can see that rest angle is being used to determine the ending angle for one of these curves or arcs, and the beginning angle for the other arc. This is also one of those things that it makes a lot more sense to see the final output rather than going through this line by line. So when we render it, there's the new solid we just created. And hopefully now you can see where all the components of the polygon are. You can see here how this arc starts at the 0 angle and then proceeds up to that calculated angle. And then on the other side, it starts from that calculated angle and it goes to 180. And that flat portion right there is 5 millimeters away from the center of the thermal terminal to fit snugly right around here. Now we're moving on to the last portion of our solid. This is going to be the hex pocket that's going to sit right on top of this terminal here, such that the thermal screw that goes in here will anchor to. Now, every time we've created a hex pocket, we've created a solid, then created a smaller solid, which is subtracted from that solid. We can use the same procedure here to create this hex pocket, but instead of doing that, what I'd like to do this time is create the solid that is the rim around this entire hex pocket. And by doing that, we actually don't need to subtract anything. Let's start it off to give a little visual of what this is going to look like. I'll create it just below the controller rest. I'm going to translate it appropriately. It's going to have a linear extrude height, which basically matches the thickness of our hex nuts. We're doing this deliberately so the hex nut can be inserted straight on over here, because otherwise there's actually no way to get the hex nut in. This will make a little bit more sense when you see the final product. Then I'll create just the first few points. We're going to use the same technique that we did for creating our arcs, but this time the step value is minus 60 degrees, because 60 degrees is the angles of the hexagon. And when you render that, we can see the first bit of this hex pocket that we've created. Just 3 points. The next portion of this solid is going to match the arc of the controller rest solid that we just created. So I'll insert another arc. Once that's rendered, you can see how we've added that arc into this polygon. Now we'll get the 2 bottom vertices. Once that's rendered, you can see how the object continued on to the bottom. Now we'll add the arc on the other side. And there it is. And then we'll finish off with the remaining points of that hexagon. Beautiful. So now we have this solid, but what about the cut in the middle to actually create the pocket? Well, there's a very good reason that I started creating this outer shell on the topmost point of that hexagon. Because if we continue to add additional points to this polygon, we can actually trace out the center cut of this hexagon, thus creating that hex pocket in the very same polygon that creates the outer shell. Like this. Add on a few more points to this polygon, this time going through all the points of the inner hexagon. And notice how the radius of this inner hexagon is smaller than the radius of the outer hexagon. And when you render that, like magic, we have our hex pocket. So maybe you're not as impressed with that. I certainly was when I tried it. I was like, I love this, I want to share it. And looking at the model, you can probably appreciate now why we had to make this hex pocket straight through. There isn't enough space in here to stick this hex nut into to sit neatly into this pocket, so we're just going to have to pass it through the bottom. Okay, so we've done a lot to our model today, but it's still not quite done. There are a few more things that we need to do to our model, but in order to do those, we're going to introduce some more advanced techniques in OpenSCAD, and we're going to do that on the next episode. Oh, I can't wait. We'll see you then.